So we're hitting another transition point. We're starting a new learning objective today. So I just want to talk about that transition a little bit. So we just got done with object-oriented programming. And of course, most of you are still working on the homework assignments. But as far as lecture is concerned, we're moving on to functional programming. So I just want to sum up object-oriented a little bit. The whole 2 weeks, the whole object-oriented programming could be summed up with pretty much one word, and that's state. Objects had state, they had state variables, and the values of those could change. Then we had those variables have different states. The state variable stored a state object, and then the type of that object would change some behavior. But a lot of behavior changing in behavior in general, depending on the state of the object on which a method is called. That state made a huge difference. As we shift into functional programming, this is going to be a bit of a hard shift. I just want to emphasize the point that object-oriented programming and functional programming, these are two different paradigms, these are two different approaches that we can use to program to write our software. There are two different approaches. There's no definitive, this one's better than this one, or anything. These are two different choices. And when we're talking about each of these, I have to artificially restrict what you can do to force you into the particular approach that we're covering. With functional programming, there is pretty much no state at all. So the thing I will restrict is that you can't depend on state anymore. So in a sense, we're going to the complete opposite end of the spectrum and saying, okay, what if we can't depend on state at all? What if everything's immutable? What if nothing can change at all? Now, how do we get things done? And of course, we're going to use a lot of functions to be able to do that. So with functions, with that in mind, we're going to talk about these 3 bullet points. Recursion, which we'll introduce Wednesday and talk about in depth on Friday. So we won't see this first bullet point, recursion, yet today. But this is when functions and methods call themselves. What we will start talking about today is this idea of first-order functions. Taking functions as parameters, having functions as return values, and just handling functions as if they were any other type of data. And how do we work with them like that? And then finally, immutability. And this immutability is, okay, what if we don't have any state? First of all, how do we get things done? And then really not until later on in the course, we'll see why we would even want to do this. So immutability, this is where we're going to talk about strings. We'll revisit strings. Before, when I mentioned strings in the terms of stack and heap, I just said, let's pretend strings go on the stack, because that's how they behave. When we talk about this bullet point next week, we want to fix that and talk about what's actually going on with strings. They're immutable objects. They do go on the heap. They are passed by reference, but since their states cannot change because they're immutable, they have the same behavior as though they were on the stack. So when you say string dot replace spaces with empty string or something like that, any of those string methods create a new string and return a reference to the brand new string that was created. So each time we call a method on a string, we're actually getting a new object on the heap and returning a reference to that new object that was just created, leaving the original string alone. And that's why they are passed by reference, but we don't get that heap reference behavior that we got with our immutable objects because it's an immutable data type. It's an immutable type. So we want to talk about those 3 things. And of course, just using functions throughout to be able to get things done still. We won't see the full payoff of functional programming. Let me back up a little bit and rephrase that. With object-oriented programming and functional programming, with each of these, I'm restricting you. It was control flow with OOP. With functional programming, it's going to be state. It's going to be bar. I'm going to take that away from you. You can't reassign values once you create a named thing. You always have to use val and not change any of that state, not have any changeable state in your objects. Your objects and classes all have to be immutable. And how do we handle that? Kind of the opposite end of OOP, from OOP. After that, I'm not going to restrict you. Data structures, algorithms, event-based architectures, and software engineering as we talk about the project. I'm not going to restrict anything anymore once I show you these 2 paradigms and how to approach designing and structuring a program and getting things done in one of these 2 paradigms. For the rest of the semester, I use more of a mixed approach for some of the requirements. With data structures, we'll use some OOP, we'll definitely use references, We'll have our data structures take functions and use functional programming. We'll use kind of a hybrid approach, a mix between the two. Whenever I don't specifically specify which approach you should take, that's when it's up to you. Which one do I want to apply? Do I want OP? Do I want FP? Do I want a hybrid of both? Or do I want to go back to 115 style and just not use either and use procedural, just lines of code, which is fine for a lot of cases. Do I want to use that approach? Do I even need something more sophisticated and more advanced? When we get to event-based architectures, that's when we're going to start getting some of the benefits of that immutability. So event-based architectures, I'll just very briefly talk about it here, is when we have, the big idea here is going to be concurrency, that we can have two things happening in our program at the same time. So what if I have two pieces of code executing at the same time? They both have a reference to an object on the heap, and they're both trying to change that object at the same time. We have these issues of concurrent writes and concurrent reads, or somebody writing while somebody else is reading. How do we handle those situations? Well, if that object on the heap is immutable, all of those issues just go away. So if we're functioning in an immutable functional programming style, when we move to event-based architectures, there are a lot of issues that we just naturally avoid by having that immutability, by having what we call pure functions, functions that don't depend on state. That makes event-based architectures very simple. And as, I didn't want to talk about this too much, but one last thing, as we move to devices that have not necessarily faster processors, but more cores, and they're doing more things at the same time. And for large apps, we have even distributed systems where multiple machines with multiple processors are working on the same problem. Think of how many pieces of hardware, how many processors it takes to run YouTube. It's more than one, I guarantee you that. It's a warehouse is filled with servers, racks and racks of servers. How do all those servers work together to deliver one single experience to millions of users simultaneously? Well, if they're depending on state, probably not so well. It's probably not going to work so good. But with immutability, functional programming, ideas of that, you can scale up to distributed systems without redesigning the architecture of your software. So that's where we're going to see a lot of the advantages of functional programming. So with that, let's talk about sorting. Yay. So sorting is one of those topics that you're just not going to get rid of. You're going to see this often. You saw this in 115, you're seeing it in 116 right now, you're going to see it again in 250, and you're probably going to see it again in 331. We like sorting. I don't exactly know why we like sorting so much, we just do. But one of the reasons is it's nice to use to motivate the topics that we want to talk about. So I'm talking about sorting today, kind of, but really what I want to focus on is first order functions. So if I use sorting, since before 115, you all knew what sorting was. You know this idea of, I have this data structure full of things and I want them sorted in some particular order. You understand that immediately. So we like to use it in each class. I think this is why we use it so much, because you know what sorting is, and we can use it to motivate the next thing that we're talking about. In 250, it's going to be in the context of big O notation and asymptotic runtimes and time efficiency and sometimes even space efficiency. In 331, it's used to motivate proofs. How do we write a proof? How do we prove that our sorting algorithm is correct? In 115, it was just how do we write code? And in 116, I'm using it for first order functions. So we use it to teach a different concept each time you see it, but you will see sorting. This is not the last time. You will see it often, over and over again. All right, so the lecture question today won't make too much sense unless you looked ahead or watched the video from earlier today. But we will learn all these things today. Write an object in a package name functions, object, generics, method, generic method. So we want to write this one method. It's going to take both a type as a parameter and a function as a parameter. It's going to also take a list of ints, and it's going to apply this function to this list, return a new list with the output of the function, which will be of the generic type, return a list of that type, that is the input list with the function applied to it. Just kind of a mouthful, kind of a lot going on. In the wording of this, But when you get to the code, if you're writing more than a few lines of code for this one, you might be on the wrong track. It's not too complicated once you actually get your get the idea of what's a type parameter, what's a function parameter. And then testing. Testing is probably a little bit harder than the question itself for this one, but it is important outside of just the testing. But how do we call this method that takes a type and a function as a parameter? I want you to get the other side of that as well. So testing, actually calling this method and making sure it does what we expect it to do is what we want to have out of this. So let's talk about what functions as parameters are and what type parameters are. And get us so we can do that question. I cannot answer that question. And sorry, Chad, I'm not touching that one. Order elements, so sorting, in case you forgot what sorting is. Ordering elements based on a certain comparator. And the key word that I want to focus on here is comparator. This is the part that you probably haven't seen of this definition before. You usually think of sorting as just sorting from least to greatest and left it at that. So the comparator is what I want to talk about. And specifically in computer science, at least when we talk about sorting, we're talking about something called comparison sort, where the only thing we can actually do is compare two elements and ask ourselves the question, does this element come before this element in the final sorted order? That's the only tool we actually have to be able to sort, and then we have to be able to sort a data structure based on just being able to ask that one question. So in Scala, we can sort, not too bad. I don't even have to use any bullet points on this slide. And we've done this earlier in the semester when we had to compare, we had a method that returned a list, and the order of the list was not defined by the problem statement. We had to do this. We called sorted on the list that we expected, sorted on the output list, and then said, are these two lists equal? And we were able to tell if those two lists had the exact same elements in them by sorting them both. For that, we just called dot sorted, and we got the expected least to greatest sorted behavior from this. But what if we want something different? What if we want a different order? I guess I want to talk about it on this slide. So this uses the default comparator, which in the case of numeric values is, in any language that I came across, I should say, is going to be the less than operator. So we're going to check, as this list is being sorted, there are going to be checks. Is 5 less than negative 23? Is negative 23 less than 7? Is negative 4 less than negative 8? It's going to ask that question until it can determine the entire sorted order of the entire list. That's what we're doing when we just call sorted. But what if we want a different order? We're going to call another method sort by, give it a method or a function, and then we're sorting the values in the default ordering, but after having that method or function applied to it. A method in this case, but we could give it a function, which we'll define function in a few slides here. So now, instead of just sorting this list, we're going to take the absolute value of each of these numbers and then sort those based on the default ordering. The default ordering of the absolute values of these things. So least to greatest, but an absolute after absolute value was called on each other. Nothing too crazy yet. Okay, but we still use default ordering for the output of these absolute values. Yes, we did. We've seen this before. This is what we want to talk about all day. But let me get to the third one first. Oh, come on. I added too many slides, apparently. What if we want to sort by something other than the default ordering? Well, for that, we have sort with. So this is like our trio of methods that we can call the Scala built-in sorting methods. Sort, sort by, and sort with. Sort with is going to take a custom comparator and then compare based on this function. These comparators are going to take two values of the type of the data structure and return a Boolean, and that Boolean is true if the first input comes before the second input in the fully sorted order, and false otherwise. So with this comparator in this structure, I can say, does A come before B? True if it does, false otherwise. So does 5 come before negative 23? This is a greater than operator. That's going to be true. 5 has to come before negative 23 in that sorted order. And this is the style of comparator that we're going to use in this class. So, and in what Scala uses. And what all our algorithms use, to be honest. So everything you've seen so far should seem pretty familiar. We're kind of used to all this from 115. Some of it comes and goes pretty quick, so it's worth refreshing. But we've seen this before. You've had Python and JavaScript sorting, where you gave it some custom comparator. The syntax is just a little different. In Python, it was usually sort by, and you'd find the keys that you sorted by. And then in JavaScript, not 100%, but I believe it was the +1, positive, negative, or 0 style of comparator. 0 if it should be, if the order doesn't matter, if they're kind of a tie. Positive if the first one comes first, and negative if the second one comes first. I always get those ones backwards, so I'm not positive if I got that. But that 3 style. For this, we're going to use the more standard, at least in the theory side of computer science, comparator of take 2 values, false if the first comes before the second, true if the first comes before the second, false otherwise. So if this is a tie, that's going to return false, and we can still get the same behavior. If we want to know if 2 values are a tie, we'll call it with, say we have 4 and 4, we want to compare just 4. We would say, is 4 less than 4? We're going to get false. And then we would swap the arguments, call it again, and say, is 4 less than 4, and get false. If we get false, no matter what the order is, then we know it's a tie, and that would be the same as getting our 0 from the other comparator. So we can still get that full functionality. Does this one come first? Does this one come first? Or does their order not matter? We still get that full functionality, even though we're returning a Boolean. So we can get that full sorted order based on this comparator. But we should return false for both orders if the order doesn't matter. So if we did greater than or equal here, it might break our algorithms. We want to make sure that equal to returns false in any case. All right. So most of that's review, unless you didn't take 115 here. That's the first time, but that's cool. We can get you caught up. But this is the part I want to talk about today. This is what we call a first order function. And we tease them, just what we've done in the last few slides. We tease these in 115. We say, look, we can give these methods functions and sort based on the output of some function. But we didn't go too in depth on how that actually worked. We kind of took it as magic. You just give it the function, and it's going to sort based on that function. Now I want to talk about the other side of that. What's actually going on when we give a function to a method? And I do mean function here. This, what I have in the green box, is finally a function. We recall that a method is something that's attached to an object, and we define those using the def keyword. If we're inside an object, we use def. We give it a name, we give it a parameter list, we give it a definition. That's a method because it's attached to an object, or we define it in a class, and then it's attached to each object of that type we create. This here is a function because it's not attached to any object. It is on its own. There's no, if inside this function I try to use the keyword this, I don't get anything. Actually, I think you do get something. I think you get the function itself, I believe, is the behavior. But there's no real state that I can access from inside this function. There's nothing meaningful that I can get out of the keyword this. So this is what we want to talk about. Sort with is going to take a function that takes 2 ints and returns Boolean and has the properties that we described. True if the first argument comes before the second one, false otherwise. And it's this function I want to talk about. So let's rewrite this a little bit. So I defined that function and put it in the method call right away. But we can tease this apart and put this on 2 separate lines, just like we could if that took an int. I could say val int, val x of type int equals 5. I could do it the same way. I'm doing the same thing here, except I'm pulling out the function. So this line right here is what we want to talk about. I'm defining a function, creating a function, storing it in a variable, value in this case, of this type, and then giving that by name to the method as my comparator. Then, of course, I get my sorted order that I expect. Because I use the greater than, so we want to sort in decreasing order instead of increasing. Nothing too interesting, but just to motivate the concept here. So let's talk about the syntax and what's going on this line here. So this, what I have in the green box, is exactly what I had in the green box in the other slide. This is exactly what was inside the parentheses. This is the function that we're creating. We're creating a function with this syntax, and then we can do whatever we want with this function. I guess it depends what you want to do with a function. But we can treat this function just like any other value in our code. So I'm creating the same function using this syntax. Parameter list in the same exact format that we've seen before. We have the parentheses, we have our names of our inputs, and we have our types separated by colons, and then each input is separated by a comma separated list. And then the body of the function is going to follow this arrow symbol. Equal, greater than, and that's the notation we're going to use to say, I'm done with the parameter list, I'm starting the definition of this function. This is similar, it's kind of similar to the notation of a map, separating the key and the value. Just a little different syntax to denote that we're starting the definition of this method. This is slightly different than, or of this function. This is slightly different than a method where we just use equals and then put the body there, because we have to differentiate this between this assignment right here. We're going to have assignments and also definitions separating between, distinction between parameter lists and definitions, and also assignments in the same line of code. We can't keep using that equal operator because the compiler's going to get tripped up. It's not going to know what you mean and where. So we have a slightly different syntax. And then finally, the body, the definition of this function. What does this function actually do? This follows the same rules as methods. The last expression that's evaluated is going to be the return value of the function. We could rewrite these. We could rewrite this using the syntax we're more familiar with. We could use these braces to define the body of the method function. I'm going to get those tripped up still, especially now that we're talking about both in the same example. We can still use the braces, especially if you have multiple lines. If you want longer definitions for your functions, you gotta use the brace notation. But with functions, it's more common. Usually we have these small functions that we're moving around our code. It's common to use the inline syntax where we just omit the braces and put the definition right on the same line, which we can actually do with methods as well. We typically avoid that syntax with methods, but we can do the same thing if we have a one-line method, and we can put it right in line like that. But if you're comfortable with this syntax, you can still use that for functions. If you want to use the shorter syntax, which I'll be using in the slides to compact the code a little bit more, you can put it right in line, which I'm going to go back to that syntax. But this is completely valid syntax and required if you want to do multi-line functions. Now let's look at this thing. What is this over here? So a function is a type, and the type is defined by the types of its inputs and outputs. So here, I have the same syntax as when I'm declaring an int. I'm going to create a value, I'm going to name it comparator, I have a colon, and then I'm going to give the type, and then assign it some value. The type for a function uses this syntax, which looks like a parameter list with only the types of the parameters, that same big arrow equal greater than, and then the type of the return value. And that whole thing in this box here is the type of the function. Comparator is a value that stores a function that takes two ints as parameters and returns a Boolean. And I define a function that happens to take two ints and a Boolean with some definition for that function. What does it return? It takes two ints, happens to evaluate to a Boolean. The last expression is a Boolean, so I'm not breaking my types. I have the same type here on the right-hand side and left-hand side of the assignment operator. and I can store that in a variable just like any other value, and then do whatever I can do with any other value. Just like this were an int or a double or a string. I can pass this around my code. I can use it as an argument to a method call. I could create other values or variables with different names and give it the same value. I can do whatever I want with this. A function is just like any other value. So this value right here is just like any other value we've seen. It's just a different type. When it's a function, for what it's worth, these are stored on the heap. They're objects. The functions are objects. Stored on the heap, passed by reference, all that good stuff that we know about those. So just like any other value on the heap, a function can be used with whatever we would do there. It's just like defining a new, creating a new object. It is, in fact, exactly that. So this is what we want to talk about for the most part, for the better part of the next 2 weeks, is this right here, and all the implications of this and everything that comes with it. Functions are just values. What can we do with that? And why would we want to do that? We won't get too much into the why until event-based architectures, like I said. A lot of the why over the next 2 weeks is going to be, how can we write, I'd say cleaner, more elegant code? That's probably debatable though. Definitely more compact code. We're going to get a lot done in fewer lines, for what that's worth. So at this point, right here, any questions about what's going on with that line there? Just for the next better part of 2 weeks, except immutability, that's a little bit of a different topic. But at least for the next 3 lectures after this one, this what's in the box is what we're going to talk about and all the implications of that. So anybody have questions about the syntax or the structure? Yes, thank you.
I don't know the syntax, but why is it exactly called a first order function?
So first order function, so it's different than the mathematical definition of a first order function. First order function in the world of programming means exactly what we're talking about here, is that a function can be treated as any other value, which is not true in all programming languages. It's one of the reasons why we use Scala in this class, because Scala does support first order functions. JavaScript and Python also support first order functions, so this might not seem like a huge revelation to you, but if you started in a language that doesn't support first order functions, it's like I did, it's a huge relief to finally have these. But that's what we call first order functions. Scala is a language that supports first order functions. If a language doesn't support these, then we just can't do these things that we're talking about. And depending on how you look at it, if you really get technical, Scala doesn't really support first order functions either, because functions are objects that simulate the behavior of a function. So it depends how technical you get. But like Java doesn't really support this. You can't really do this in Java, except the newer versions of Java are starting to have some changed syntax that kind of pretends that there are first order functions. So these days, with functional programming becoming more popular, most languages are supporting it. So first order functions are kind of just functions these days, I suppose. But that's why, if you can't do this, then you don't have first order functions in whatever language you chose. All right, let's look at some implications of this. Any other questions on this line? Let's look at some implications of this. First one's a juicy one here. If you're working on a calculator, I have that hint near the end of the document that says it's an advanced hint. Well, at this moment, it's not advanced anymore. It's just the regular what you know how to do at this point, now that you know first order functions. So you have this question of, when I hit the equal sign, which of the 4 operators should be used, if any? Sometimes it doesn't do anything. But which of the 4 operators should be used for that evaluation? And there's a temptation to create a new state for each of the 4 operators and have an X4 blow up in certain states. And you can easily have 10, 14, 16. I've seen like 30, 40 states in some submissions. It's easy to get that kind of blow up if you have separate states for each of your operators. But with first order functions and with function variables of function types, you can do something like this and store that operator that should be used for the next evaluation in a variable, and then say, hey variable, whatever your operator you're currently storing, evaluate it. And this is, there's something carefully crafted in the assignment to make sure you can do this, in that every operator is a binary operator, and every operator takes two doubles and returns a double. So since every operator has the same input types and output type, you can have a function of type double and double to double, and then define, set that equal to the value of each one of your operators, depending on which buttons are being pressed and what's the state of your calculator and all that. All the state logic you still have to do, of course, but just to remember which state, which operator should be the next one to be used if someone is to hit the equal or an operator, depending on the state and everything. Store that in a variable. And back to sorting, we only sorted ints so far, but what if we want to sort something else? Well, sort with just works. If we give this sort with a comparator, and in this case I'm even giving it a method, methods will work as functions. I'll give this a method, compare animals, takes two animals and returns a Boolean, and sorts them by their name, ignoring case. And the less than, greater than, that works with strings, it'll do the, it'll sort by their ASCII values, I'm pretty sure, to get that ordering. So I'm gonna two lowercase them and then do less than to get rid of the alphabetical, or the uppercase, lowercase differences. And then I can sort these, call sort with, compare my animals based on this. I didn't show this code in lecture before, but you can kind of imagine cats and dogs both extend animal, and the name state variable is part of the animal class. So I can sort, given a comparator, as long as it takes two animals and returns a Boolean, it's going to sort with that comparator. This is the functionality, the sort with. That's the functionality that we'd like to see how that works. How did that handle a different type? Shouldn't sort with only work with certain types or some sort of inheritance or something? That's what we want to talk about. Spoilers, the answer will be type parameters for that one. But how does all this work? Let's talk about how it works. I'm confused on why you would use first order functions on the calculator. I mean, you don't have to, but it can really limit the complexity of your design. It can really help you out with that design. So let's, if that didn't make sense to you, just don't use them. It's fine. You'll still get through the assignment. So let's talk about selection sort. You talked about this briefly in 115. It kind of came and went real quick, and then you were never held accountable for that information. So I want to kind of revisit this and talk about selection sort, and specifically how selection sort gets the job done. So we have some input. We want to sort them by the default ordering. We'll just stick to the default ordering, which means we're using less than as our comparator, which will give us this type of ordering. So for selection sort, what we do is start with the first index. We go through the whole list, figure out the minimum value, and then swap the first value with that minimum value. But to get this done, we have to remember with comparison sort, all we have is a comparator that takes two values matching the type of the list and returns a Boolean if the first value comes before the second one and false otherwise. That's all we have. So what we have to do is say, assuming we're given the less than operator as our comparator, we're going to say, is 5 less than negative 23? Which is to say, should 5 come before negative 23 in this sorted order? False, so I'm not going to do that. Or rather, actually, let me talk about it the other way because that's how my code is set up. Is negative 23 less than 5? That's true. So once I get it true, I'm going to say, okay, this is the minimum value that I found so far. Then I'm going to say, is negative 8 less than negative 23? False. Is 7 less than negative 23? False. Is negative 4 less than negative 23? False. Is 10 less than negative 23? False. So when I get to the end of the list, the value that I was comparing to the other values was still negative 23. So I'm going to swap negative 23 and 5 to get this list in the end. But throughout all that, the only thing I did was call less than on pairs of values. All I can do is compare two values, and I have to use that function to be able to sort an entire list. So we do that over and over. Negative 23, we compare that to all of the other values, either directly or by transitivity. So we know negative 23 comes before everything else. So that's our first value. So we lock that in. We look at the rest of our list. We say, is negative 8 less than 5? True. 7 less than negative 8, so on and so on. Find negative 8 is the next value. Is 7 less than 5? False. So we compare 5. Negative 4 less than 5? True. Is 10 less than negative 4? False. Negative 4. And so on and so forth. Until we get to the end of the list. We get a completely sorted list using only that one comparator. So if we look at the code to do that same thing, we're doing what I showed in the slides. We're finding the minimum value for each index and checking, this value I'm looking at come before the value that I found that comes before all the other ones that I haven't checked. That's an awkward sentence I just crafted there. But the only thing we need to know is how to compare two values. It's the only thing we need to be able to get our sorting done. So what we can do is write a sorting method or implement a sorting algorithm. Implement selection sort is a method in this case that takes a list that we want to sort and the comparator that we want to compare. So if we want to do the sorting that we just did in the other slides, we would give it some list of ints and then the less than operator as a comparator. So we took this function as a parameter. So remember, functions, we can use them just like any other value. I'm going to take a function, I'm going to name it comparator. This is just like any other parameter, except the type is a function that takes two ints and returns a Boolean. So I don't care what this comparator does. When I write my algorithm, I don't care if I'm sorting less than, greater than, by absolute value, by how close they are to 50, or how much you like the number and you rated every number. I don't care what this comparator is doing. I'm just going to use that comparator that I'm given at runtime and use that whenever I need to compare two values. So there's only one spot in this code where I'm comparing two values, and I'm going to call this comparator just like a method call. I'm going to take that comparator, that variable of type of name, that variable named comparator of type int and int to Boolean, give it two ints. That's going to resolve to a Boolean. I don't care what happened in between. I mean, I kind of do. I hope that they're following the protocol for a comparator, or else I'm going to get some really wacky ordering here. But I don't really care what it does. I don't really care how I'm sorting when I implement this method. This has a lot of advantages. We get one method that can do a lot of different things, similar to our objects can do a lot of different things depending on their state. This method can do a lot of different things depending on the function that we're given. So we're kind of abstracting out some of the functionality. This comparison here, we're abstracting that out and saying, give me this piece of the functionality when you call me. Just give me some function and I'll call it. When you call me, I'll call your function that you give me, and we're going to get a lot of different behavior depending on what you give me. And we call this with the same syntax as a method. Argument list, comma separated values, match the types, and we get there. So to call this method, we'd use the same syntax as sort with. We just have it set up a little bit different than the sort with because that was a method in the list class. Now we're going to call selection sort, give it some list of numbers, some list of ints, give it a comparator. Here we use greater than to get the decreasing order of the sort. And when I give it the greater than method, or the greater than function, it's going to give me a completely different sorted order is when we use less than, but I didn't have to change any of my code. So we can write this method, test this method, make sure this works the way we expect it to, and then get a lot of different behavior out of it, just based on giving it different functions as parameters. But only writing and testing it once and not having to change that code when we expand the functionality. So a lot of the goals are the same as OOP. Write something once, test it once, get a lot of mileage out of it. Same thing here, just a little different setup. Whereas if we want a decreasing order, increasing order as two separate methods and test them, it could get messy. But we didn't get all the way there yet. How do we sort this? How do we get this behavior out of our selection sort? So how do we sort these animals based on a custom type that we wrote without writing int selection sort, animal selection sort, double selection sort, string selection sort? How do we do that without getting really messy here? And for that, type parameters. So type parameters, we've been using these throughout the course. Every time you create a list or a map or an array, you're using type parameters. But now let's look at what's going on the other side of that. How do we write things that take type parameters? So type parameter, you're going to put your type parameter list right before your regular parameter list. And you're going to use brackets instead of parentheses. You're going to put any name you want. You can name this whatever you want, just like any other argument. This is like a variable name, but you're not giving it a type. It actually is itself a type. And you're going to put that right there with that syntax to say that this method does not have fully defined type. You have to provide the type when you call this method. So we specify the type and then use that type throughout the method. So this type, we don't know what it's going to be when we write this method, and we don't care. It could be anything in the world. But it has to be consistent throughout the method. So if somebody specifies a type, maybe they want int to get the behavior that we had before, then they have to give us a list of ints, a comparator that takes two ints, and this is going to return a list of ints. So we can specify all that at runtime. And most of our code is the same. I just compacted it a little more. Most of our code is the same. The only difference is we create a list of whatever type we get at runtime. Not caring what that type is, but we just create a list of that type at runtime. And we usually shorten these to one character. It's just convention, and don't ask me why. But it's common to use names that are just a single character long. T for type in this case. A and B are common. K and V if it's a map. If you look at the map code, K and V are the names of their type parameters there. But we typically use these single variable names, single character names. So T, whatever T is, we're going to use that type throughout our method. And finally, to call this, there's really not much different when we call this. Like I said, you've been using methods that take type parameters all throughout the course. If you do append to a list, and that list is a list of ints, that type parameter is int for that method call, for that append method call. If you're splicing a list or anything else you're doing to a list, I'm blanking on my list methods right now. But those all take type parameters of that type of the list that you're calling it on. But you don't always have to specify the type parameter. In fact, it's fairly rare that you have to specify the type parameter explicitly, except when you're saying the type of a list and type of a map when you're using that as a variable, or a parameter or a return type. This method that takes a type parameter can be inferred by Scala. So selection sort, I'm giving it a list of animals, and I'm giving it the compare animals method, which took two animals and returned a Boolean. So Scala is going to look at this and say, well, you gave me a list of animals, your comparator takes two animals, I think your type parameter is animal. So once it figures that out, you don't have to explicitly say the type parameter. You would put it right here in brackets. You would say, in brackets, animal, and then call the method, which sometimes you'd have to do. For example, if you had a list of just cats, and a list of type cat, but you wanted to use the animal comparator, Scala might get a little confused. You might have to specify that I'm using animal as my type parameter, not cat. Scala might be able to figure that one out. I'm not sure. I'd have to try it. But in most cases, all your types match, and Scala just says, I know what your type parameter is. You don't have to tell me explicitly. So, but this is a method called T is animal, list of animal, comparative animal to animal, returns a list of animal, and this will be a list of animal, which is decided when the method is called. Any questions on the type parameters? Yes.
If, let's say, one type is int and the other one is double, and when passing in the function, is there some sort of like type invariance?
If one is int and one is, like if this is a list of int and I'm comparing a comparator of doubles, there are cases where there would be implicit type conversion. I don't think that would be one of them. I think you'd have to explicitly convert your list over in that situation. You'd have to create a list of doubles, copy in all your values, and then use that in the method call. I don't think that one would do it for you. You'd have a little extra work to do there. But we will see, kind of related to that, we will see multiple type parameters where maybe you do want to take in a list of ints and return a list of doubles, but you want your method to be completely generic to convert to between any two types. We would use two type parameters for that. Like a map uses K and B, keys and values, two types. We'll do the same thing. And finally, just kind of a note, just kind of setting up next lecture. The selection sort we saw is extremely slow, and I don't just mean in 115 you saw that selection sort is an n squared algorithm. I mean this thing is terribly slow because if you trace through that code, I am creating a lot of additional lists. I'm pretty sure my implementation is actually end of the fourth, and those are things that we're going to talk about Wednesday. We're going to talk about a more efficient algorithm. We'll talk about merge sort and how that works, and then when we talk about linked lists later on in the course, we'll see how to get rid of that blow up in copying these lists and having tons of lists all over our heap space. So more about that coming up. Lecture question. I'll see you when.